Okay, we ended the last video talking about the ideal Carnot heat engine. So Carnot is this guy right here. He was a Scottish scientist that came up with the perfect engine. And what would be required for a perfect engine is zero temperature lost or not being used, which means not just 0 degrees Celsius, but 0 Kelvin. So we're talking absolute zero here. So that's impossible. We cannot recreate a Carnot engine, but that is the ideal perfect, and we can try to be as close to it as possible, although we can never achieve it. The best engines right now run at about 60 to 80% of the ideal Carnot engine. So let's take a look at this. So we know that a Carnot engine is ideal but unachievable. So that might help us to solve this problem here. A new engine manufacturer makes a claim that their heat input per second, so that's the QH, the heat going in, the high heat, is 9.0 kilojoules at a temperature of 435 Kelvin. So that's the high temperature. The heat output is 4.0 kilojoules. So that's the Q low temperature coming out the tailpipe, or not temperature, but heat. And the temperature is 285 Kelvin. So that's the temperature low. Do you believe these claims? Does this sound reasonable? Well, let's compare it to what a Carnot engine would be. If this engine were running perfectly, perfect expansion, perfect compression, then what would its efficiency be at those temperatures? So Carnot efficiency is QH, actually just efficiency is QH minus QL over QH. So that's equal to 9.0 kilojoules. Erase that. That's looking, I got a little sloppy there. All right, let's try a little better. Kilojoules, there we go. Minus the low heat, 4.0 kilojoules, divided by the 9.0 kilojoules. So this is the efficiency of their engine. The efficiency of their engine is 0.56, or 56% is their efficiency. Okay, which, as I said here a couple slides back, it is possible to get into the 60 to 80% Carnot efficiency. So maybe they can do that. But let's take a look at if we did have an ideal, perfect Carnot engine, what would its efficiency be running at these temperatures? So the efficiency ideal, like the perfect efficiency given these temperatures, is going to be the high temperature minus the low temperature divided by the high temperature. So that's 435 Kelvin minus 285 Kelvin divided by 435 Kelvin. So if this were a perfect Carnot engine and these were the high and low temperatures, we would expect an efficiency of 0.34 or 34%. So in other words, at these temperatures that were given, this is the best it can possibly get, is 34%. So if the engine manufacturer is telling us that they're getting 56%, they are lying. That is impossible. That is physically impossible. Can't be done. So let's move on now to talk about refrigerators, air conditioners, and heat pumps. So some of you may have a heat pump in your home, and essentially what it is it's an air conditioner running in reverse. So I mentioned before, heat always flows from hot to cold, not cold to hot. So a refrigerator or freezer doesn't add coldness to a system, it removes the heat. It sucks the heat out of, like when we were talking about making ice cubes, you put an ice cube tray full of water into the freezer, it sucks the heat out of those out of that water uh, until it turns into ice and then cools the ice, and the heat comes out the back. Let me advance the slide here. Out the back of the refrigerator. So we have a motor here that's doing work on the system, and it's pulling temperature out of the refrigerator, or energy out of the refrigerator, and it is exhausting out the back of it a high amount of energy. And for those of you too young to remember, this is refrigerator Perry. So essentially, it's a heat engine running in reverse. Rather than having something that does work, we are doing work on the system. We're putting work into it. And that's going to draw heat energy, low heat energy, and exhaust a higher amount of heat energy out the back. So by doing work on the system, we can pull heat out of it, leaving behind something cooler. So if we're talking about air conditioning, we're cooling the inside of a house. A refrigerator, we're cooling the inside of the refrigerator itself. Or with a heat pump, the heat pump actually works. Let me jump to the next slide here. A heat pump is pulling energy from the outside. And you may think, well, in the wintertime, there's not that much heat energy out there. That's true, but there is still enough. There's still enough energy in the ambient air that if you do work on it with a heat pump, you can pull that energy out and exhaust that larger amount of heat into the house and heat it. It's just air conditioning in reverse. So the coefficient of performance here for a refrigerator or heat pump, or anything along those lines, which is basically a heat engine working in reverse. So this is similar to efficiency. The coefficient of performance is the low heat value divided by the work that you need to do on it in order to pull it out of the system and create that high heat exhaust, which in this case, the exhaust, in a refrigerator, we're pulling it out and getting rid of it. In a heat pump situation, that exhaust is actually what we want in order to heat the house. So taking this and doing some substitution, work is equal to the difference between high and low heat. That's the first law of thermodynamics there. And so we can make that correspond to an ideal situation, the Carnot type ideal perfect thing, where we've got low temperature corresponding to low heat, high temperature corresponding to high heat, and low temperature here. So we can figure out what is the ideal that we would like to achieve using that equation right there. Okay, so I already said a heat pump works on a very similar principle to air conditioning or refrigerator. It's pulling heat energy from outside and exhausting it in. So instead of cooling a freezer, we're actually heating a house by doing work. All right, this is going to bring us now to one of our final topics of the semester, and it's the ideal of entropy. And if you'll recall the second law of thermodynamics, essentially is saying there are some processes in the natural world that can only occur in one direction. We had that image of the coffee mug falling off the counter and breaking on the floor. That's a perfectly natural process to occur. What would never occur is that those broken shards would go back together and jump back up onto the countertop. That just doesn't happen. And so entropy is basically saying that as these thermodynamic processes occur, there is some waste energy. Now, that might seem at first as if that violates the law of conservation of energy that says energy cannot be created or destroyed, only change from one form to another. And that's true, that still holds, but not all energy is created equal. Some energy is useful, that can be used to do something you want, and other energy cannot. It is like the broken shards of coffee cup on the ground. We can't make them jump back into a whole coffee cup again. They've been used and they've been turned into other things other forms of energy that are not useful to us. And so entropy is this idea that in the natural world things become less organized, more chaotic, more disordered. And we measure we measure entropy with the letter S. This is entropy. And we can really only ever measure a change in entropy. Think about your bedroom at home. It has a tendency over time to get more disordered and more messy. Your clothes don't accidentally fold themselves and jump into your drawers. That just doesn't happen. Things tend to naturally get more disordered over time. But we can never say at any one given point in time how ordered something is. We can't give it a finite or definitive number, but we can compare it to what it was before. So we can describe a change in entropy, but we can't actually quantify entropy. So a change in entropy is equal to Q over T. So heat over temperature. So it's a measure of the disorder of a system, as I said. This is kind of a cool image I found online where the organized pixels here, as you move to the right, become more and more disordered. And so natural processes tend to move towards a state of greater disorder. That's just a natural law of the universe. So some examples provided by the book. If you put milk and sugar in your coffee and stir it, they get mixed up. But you're never going to stir it to the point where they separate themselves. If a tornado hits a building, it tears it apart. But you would never be able to just buy a pile of lumber and wait for a tornado to come along and build you a house. So that continues with this idea of thermal equilibrium. The final state after a thermodynamic process is carried out is more disordered than it was originally. So essentially, it's not entirely accurate to put it this way, but in a way, we're kind of running out of energy or useful energy. The energy in the universe is becoming more and more disordered. And so eventually, we're going to run out of the ability to have useful energy. And I'll post a video, it's embedded in my PowerPoint on Blackboard, that shows how eventually, when the universe runs out of useful energy, that is a phenomenon that will happen in the future called the heat death of the universe. So that is going to happen. The universe is going to die at some point. But not to worry, it will be billions and billions of years in the future.